Greetings, gang, and welcome back to Chapter 15, where we're going to be talking a little bit about temperature today. Now, we already know that the particles of any given substance tend to move around. For gases and liquids, obviously, they move around quite a bit, even relative to each other. But even the particles in solid matter vibrate. The greater the motion of the particles, the greater the kinetic energy. Thus, the greater the kinetic energy of the particles in a substance, the greater the temperature. But temperature is often defined differently in different places, regardless of the fact that temperature really is a matter of the average kinetic energy of a substance's particles. The temperature scale that we're generally used to here in the States is Fahrenheit. Fahrenheit is kind of a funny thing. The freezing point of water is 32 Fahrenheit. The boiling point of water is 212 Fahrenheit. So why is it like this? Well, the person who was contriving this scale, Herr Fahrenheit, wanted to try to make a scale such that 0 would be where the freezing point of water is, and 200 would be the boiling point, and at 100 was supposed to be body temperature. But it's not like that. I'm sure you guys all probably know that your body temperature is closer to about 98.6, not an even 100. And also, the freezing point of water is not 0, it's 32, and the boiling point of water is not 200, it's 212. So, it just so happens that the amount of temperature difference in between freezing and boiling does not find a halfway point exactly at human body temperature. It's decently close, but it's not exact, and so the temperature scale is all goofy. In any case, these temperatures aren't exactly even in proportion, and so we ended up with some really funny numbers. But just note that the difference in between these two is 180 degrees. Generally, the rest of the world uses a completely different temperature scale, that which we call centigrade or Celsius. In this temperature scale, 0 degrees C is the freezing point of water. And the boiling point of water is 100 degrees C. And that's a difference, of course, of 100 degrees, right? That means essentially that 100 degrees C is equal to 180 degrees F, or 1 degree C is 1.8 degrees F, or 1 degree C is 9/5 of 1 degree F, or 1.8 degrees Fahrenheit. And it is for that reason that if we want to have a conversion in between these two units, it goes something like this. Fahrenheit is equal to 9/5 of your centigrade temperature plus 32. Whereas centigrade or Celsius is 5/9 your Fahrenheit temperature minus 32 degrees. You'll notice that there's a 32 degree offset at 0 here, right? And that's where this plus or minus 32 comes from. Now, we don't always use degrees C in science for one very simple reason. The temperature at which all kinetic energy in a substance leaves is this temperature, this very special temperature that we call absolute zero. Because when all of the kinetic energy in a substance leaves, the particles stop moving altogether, and they are no longer able to hold themselves in the form of matter. And at that temperature, matter is supposed to stop existing. This absolute zero temperature is something like minus 273 degrees C, way down here. But we have a special a special system for this absolute temperature we call Kelvin. And at 0 Kelvin, we have this absolute zero, this minus 273 degrees C temperature. Okay, well, if absolute zero is at minus 273 degrees C, 0 degrees C has to be at 273 Kelvin, right? 100 degrees C has to be at 373 Kelvin. Long story short, 1 degree C is equal to 1 Kelvin. Not degrees Kelvin, just Kelvin. So why is it that something either feels hot or cold to the touch? Well, because a special kind of energy called heat can transfer in between objects. The heat, say, going from your hand into ice, or heat going from a hot fork into your hand, will transfer some heat into your hand. You can feel the hot fork or the cold ice, right? It feels cold because it's taking some of your heat. It feels hot because it's imparting some heat to you. In the cases, excuse me, of the ice and the fork, respectively. Matter can have heat energy, but there are also other kinds of energy, like Gibbs free energy, electrical energy, chemical energy, but we're going to limit ourselves to heat for now, okay? So suffice to say that heat goes from hot objects to cold objects until they are in equilibrium. That is, they're at the same temperature. And at that point, something will just feel lukewarm to you, right, if it's at your body temperature. And you don't impart any heat to it, and it doesn't impart any heat to you. So if heat is energy, what are the units? Well, regardless of the kind of energies that we talked about before, gravitational potential energy, kinetic energy, whatever, they all had units of joules, right? And so heat energy has to be measurable in joules also. Now, it is quite often that sometimes we also use another unit, this funny thing called a calorie. And a calorie is the amount of heat required to heat 1 gram of water by 1 degree C. 1 calorie is equal to 4.19 or so. It's like 4.186 joules. But does it take up 1 calorie to heat up 1 gram of everything by 1 degree C? No, of course not. You already knew that, of course, because you've been to the beach, right? In the middle of the day, the sand is usually hot, too hot to walk across barefoot. But the water, especially if you go down to Santa Cruz, is always really cold, even in the summer. We said that the sand and the water have different specific heat capacities. Or sometimes we just say specific heat for short. So the sand and the water have very different specific heat capacities. The water has a very high specific heat capacity, meaning it takes a whole lot of heat and energy to try to heat up the water. Whereas the sand has a very low specific heat capacity. It only has to absorb a little bit of heat in order to change its temperature a lot so that it's really uncomfortable to your feet, right? The water takes so much more heat to change its temperature, and so it has a much higher specific heat, which is why typically we use water for cooling systems and things like that. But what else is a factor in how much heat is required to change the temperature of an object? Well, obviously, if you want to talk about the amount of heat required in order to change the temperature of an object, one of the things that's going to be a factor is how massive the object is, right? If you wanted to heat up 1,000 gallons of water, it's going to take a lot more heat than 1 gallon of water, right? I'm sorry, I should have said 1,000 liters. We don't talk about gallons in this class. Or in science in general. In any case, what else? Well, if you wanted to change the temperature of 1 liter of water by 10 degrees, would you have to add the same amount of heat if you wanted to change that exact same amount of water's temperature by 50 degrees instead? No, you need to add 5 much times as heat, right? And so the change in temperature is also a factor. And finally, that last thing that we said, the specific heat required, right? The specific heat capacity of a substance is going to tell us something about how much heat is going to be required in order to change the temperature of the object, right? Thus, the heat required to heat up an object is equal to the mass of the object times its specific heat capacity times the change in temperature, or how much temperature change you want to affect in this object. Now, substances, when they heat up, they expand. Why is that? Well, remember that the temperature is a measure of the average kinetic energy of the particles in a substance, right? The more the particles move, the more space they're going to occupy, because they're going to push up against each other, bounce against each other, vibrate, and expand. And this is why bridges like the Golden Gate Bridge have those expansion joints. And if you look at them in the winter, right, these things are like, the teeth are further away, but in the summer, they like grow together, right? They consummate. And that keeps the bridge from expanding too much and breaking, right? Destroying itself. And so on hot summer days, the bridge can expand into itself without breaking. And then it can shrink and freeze back down without the cars falling off. That's why we have these expansion joints on bridges. Generally, the hotter something is, the higher the temperature, the more it expands. But there is one substance in particular that doesn't quite follow this model. And that, of course, is water. If you wanted to graph the amount of volume that water occupies under, 1 atmosphere of pressure here near sea level at various temperatures, we'll plot increasing temperature in degrees C this way. We'll say 0 degrees C is here, and this is like 100, right? Now let's say you've got some water, right? When it freezes, it actually increases in volume. Water is actually less dense, right? The volume that water occupies is greater when it's frozen. And that's why ice floats, because it's less dense than the water around it. But 0 degrees C water has a certain amount of volume, right, per unit mass. But water is actually its densest around 4 degrees C. And then after that, it picks back up and increases until it vaporizes and occupies a whole lot of volume, right? But it's densest right here around 4 degrees C. When water freezes, it van der Waals and makes a crystal structure where the molecules, on average, are farther apart, becomes less dense, and takes up much more room, and that's why ice floats. But when water warms up and melts, it changes volume, and then it becomes its most dense around 4 degrees, and then if you heat it up after that, it expands like the rest of most normal matter does. And if you remember our heating water demo, you'll remember this quite vividly. Now this is good news for you if you are a fish. Why is this good news for you if you're a fish? Well, you can imagine that if you're living in, say, a lake, right? And the lake is, it's got a water line up to here, something like that. And you're this fish. And you're living in this lake. Now, if you live in this lake most of the year, it's probably just, a lake. But in the winter, in all likelihood, no matter how cold it gets, probably the entire lake is not going to freeze. because that would take a tremendous amount of heat out of the water, probably more than can be taken out in just a couple of months. It would need to be constant to freeze all the way through, right? So in between fall and spring, you may get a layer of ice, and then if it's a really bad winter, the layer will continue to get thicker and thicker and thicker and thicker. But it would take a whole lot, like a nuclear winter or something, that somehow became permanent for it to freeze all the way through. Now, why is that good news for you if you're a fish? Well, if you are a fish and you're in this lake and your body temperature goes all the way down to 0 degrees C, to the freezing point of water, the water in your body will freeze and you will die. But you can't die at the bottom of the lake, because water is its densest at 4 degrees, and so down here at the bottom it's probably going to be around 4 degrees C the whole time. And so if you're a fish and you're in a lake, even if it's freezing over, you can just swim down near the bottom where it's going to be closer to 4 degrees C and survive. In any case, I hope you've enjoyed this video. I'll see you again soon for chapter 16.